In this lesson, we will look at increasing and decreasing functions and the first derivative test. Derivatives can be used to classify relative extrema, which are relative maximum and minimum points, as either relative maxima or relative minima. The textbook definition for increasing and decreasing functions states that a function f is increasing on an interval if for any two numbers x1 and x2 in the interval, x1 being less than x2 implies that f of x1 is less than f of x2. Similarly, a function f is decreasing on an interval if for any two numbers x1 and x2 in the interval, x1 being less than x2 implies that f of x1 is greater than f of x2. A function is increasing if, as x moves to the right, its graph moves up. It is decreasing if its graph moves down. Our test for increasing and decreasing functions is going to involve the first derivative. Let f be a function that is continuous on the closed interval from a to b and differentiable on the open interval from a to b. If f prime of x is greater than 0 for all x in the interval, then f is increasing on the interval. If f prime of x is less than 0 for all x in the interval, then f is decreasing on the interval. And if f prime of x equals 0 for all x in the interval, then f is constant on the interval. So in other words, if the derivative is positive, then the function is increasing. If the derivative is negative, the function is decreasing. And if the derivative is 0, then the function is constant at that value. Recall that local extrema, maxes and mins, occur at critical points. A function may change direction from increasing to decreasing at its critical points. Here are the guidelines for finding intervals on which a function is increasing or decreasing. If f is continuous on the closed interval from a to b, then to find the open intervals on which f is increasing or decreasing, we will use the following steps. First, locate the critical numbers of f on the open interval from a to b and use those numbers to determine test intervals. And remember, our critical numbers are the values where the derivative is either equal to 0 or undefined. Next, we determine the sign of f prime of x, the sign of the derivative, at one test value in each of the intervals. Next, we decide whether f is increasing or decreasing based on the sign of the derivative. If the derivative is positive, the function is increasing. If the derivative is negative, the function is decreasing. These guidelines are also valid if the interval from a to b is replaced by an interval of the form from negative infinity to b, from a to infinity, or from negative infinity to infinity. Let's look at an example. Find the open intervals on which f of x equals x cubed minus 3x squared is increasing or decreasing. First, we must locate the critical numbers of f. Remember, these are the values that make the derivative equal to 0 or undefined. Using the power rule, our derivative is f prime of x equals 3x squared minus 3x. If we set this derivative equal to 0 and solve for x, we find that our critical numbers are 0 and 1. Next, we will use these critical numbers to determine test intervals. Our test intervals will be from negative infinity to 0, 0 to 1, and 1 to infinity. So we have an interval on each side of each of our critical numbers. So here we have formed a table where we have our intervals. we're going to choose a test value in each interval, examine the sign of the derivative, determine if it's positive or negative, and then based on that, conclude whether or not the function is increasing or decreasing. So for example, on the interval from negative infinity to 0, a good test value might be negative 10. If I replace the derivative, if I replace the x in the derivative with negative 10, 3 times negative 10 would be a negative, negative 10 minus 1 would be a negative, and a negative times a negative is a positive. So on this interval, f of x is increasing. From 0 to 1, 1/2 would be a good test value. 3 times 1/2 is positive. 1/2 minus 1 is negative, and a positive times a negative is a negative. So the derivative is negative when x equals 1/2. Therefore, on the interval from 0 to 1, f of x must be decreasing. And our last interval is from 1 to infinity. Positive 2 is a value in that interval that we could use as our test value. 3 times 2 is 6, a positive number. 2 minus 1 is 1, also a positive number, and a positive times a positive is a positive. So on the interval from 1 to infinity, this function is increasing. Since the function is changing from increasing to decreasing at x equals 0, this is the location of a relative maximum. And since the function is changing from decreasing to increasing at x equals 1, this is the location of a relative minimum. If we were to sketch the behavior of this function, it goes from increasing to decreasing to increasing. So you can see that when the function changes from increasing to decreasing, that is the location of a relative maximum. And likewise, when it changes from decreasing to increasing, we have a relative minimum. This leads us to the first derivative test. Let C be a critical number of a function f that is continuous on open interval I containing C. If f is differentiable on the interval, except possibly at C, then f of C can be classified as follows. If f prime of x changes from negative to positive at C, then f of C is a relative minimum of f. And if f prime of x changes from positive to negative at C, then f of C is a relative maximum of f. Here are the graphical examples. We can see that the slope of the tangent here is negative, where the function is decreasing. When the function begins to increase, the slope of the tangent becomes positive, and so that change in the value of the derivative from negative to positive indicates a relative minimum. This works in much the same way for the maximum. When the slope of the tangent line changes from positive to negative, that indicates that the function itself is changing from increasing to decreasing, which indicates a relative maximum. In the lower graphical examples, the function in this case goes increasing and it continues to increase. The derivative remains positive. It temporarily becomes 0, but then it continues to be positive. So there's no relative or maximum minimum. And same with this one, we've got a continuously decreasing function. Derivative is either 0 or negative on the entire interval, and so there's no relative min or max. Find the relative extrema of the function f of x equals 1/2 x minus sin x in the interval from 0 to 2 pi. First, we need to find the critical numbers, so we'll begin with the derivative. The derivative of this function is f prime of x equals 1/2 minus cosine x. So for finding the critical points, we'll set this equal to 0 and solve for x on the interval from 0 to 2 pi. This means we're looking for the points where cosine x equals 1/2. On the unit circle, remember that cosine is given by the x-coordinate of the point on the unit circle. And we can see that the x value of these coordinates is 1/2 at pi over 3 and 5 pi over 3. So those will be our critical values between 0 and 2 pi. So next we have our intervals established from 0 to pi over 3, from pi over 3 to 5 pi over 3, and from 5 pi over 3 to 2 pi. And we're using 0 and 2 pi as the endpoints because they're the endpoints of the interval we're interested in here. So in choosing a test value, if we, for instance, choose pi over 4 for our test value in the first interval, 1/2 minus the cosine of pi over 4. You can quickly generate that on your calculator. We're just looking to see whether it's positive or negative. That's a negative value, and therefore the function will be decreasing on that interval. From pi over 3 to 5 pi over 3, pi might be a good value within that interval. 3 pi over 3 would be equal to pi. We already know that the cosine of pi is -1. So when we plug this in, 1/2 minus the cosine of pi, that's 1/2 minus -1. And so that's really like adding 1, and it results in a positive. So on this interval, our function is increasing. And for the third interval, let's go with, let's see, 6 pi over 3 would actually equal 2 pi. And 5/3 pi is about 5.2. So I'm just going to use 6 as the test interval because I know that's not quite 2 pi, but it's larger than 5 pi over 3. And if I use my calculator and evaluate 1/2 minus the cosine of 6, I get a negative. And therefore, the function is decreasing on the interval from 5 pi over 3 to 2 pi. So therefore, there is a relative minimum at x equal pi over 3 because the derivative changes from negative to positive. The function, notice, changes from decreasing to increasing. There's a relative maximum at 5 pi over 3 because the derivative changes from positive to negative. The function changes from increasing to decreasing. Okay, and for our last example, let's find the relative extrema of f of x equals x squared minus 4 to the 2/3. First, we need to find the critical numbers. F prime of x equals 2/3 times x squared minus 4 to the -1/3 times 2x is our derivative based on the chain rule. We can simplify that as follows. 2 times 2x is 4x in the numerator. The denominator becomes 3 times x squared minus 4 to the 1/3. That exponent becomes positive when we move to the denominator. So we now need to see where this derivative is equal to 0 or undefined. To find out where the derivative equals 0, we can set the numerator equal to 0. And to see where the derivative is undefined, we set our denominator equal to 0. So we find that these values are at x equals 0 and at x equals positive or -2. So these are our critical numbers. So here we have our table, and we will proceed with determining a test value, finding the sign of the derivative, and then determining whether the function is increasing or decreasing on that interval. From -infinity to -2, let's go with -3 as our test value. The numerator of this would be negative if we let x equal -3. The denominator, this would be -3 squared minus 4, which would be a positive value. 9 minus 4 is a positive. So the denominator would be positive, meaning that this would be negative. And so the function is decreasing on that interval. From -2 to 0, -1 would be a good test value. If I plug -1 in for x in my derivative, the numerator will be negative. The denominator will also be negative because -1 squared is 1. 1 minus 4 is a negative. The cube root of a negative is negative, and 3 times a negative is negative. And so a negative divided by a negative is positive, and that means that the function is increasing on that interval. From 0 to 2, I'm going to choose 1 as my test value. The numerator will be positive, 4 times 1. The denominator will once again be negative because we will again have 1 minus 4 resulting in a negative, cube root of a negative, and that is also negative. So this positive divided by a negative is negative, meaning that our function is decreasing on that interval. And from 2 to infinity, I'm going to choose +3 as my test value. 4 times 3 is a positive in the numerator. 3 squared minus 4 will be a positive in the denominator. And so this interval is positive, and therefore the function is increasing. The function has a relative minima at x equals 2 and at x equals -2 because this is where the derivative changes from negative to positive. The function has a relative maximum at x equals 0 because this is where the derivative changes from positive to negative. The relative minima are at the points 2, 0, and -2, 0. And those are found by plugging the x values back into the original function. Because remember, these max and min points are on the initial function and not the derivative. The relative maximum point is at 0, cube root of 16. If we plug 0 in for x, we get cube root of 16. And here is the graph that we can view to confirm this. And you can notice these 2 points are where the derivative is undefined, and we can see that these can also be minimum points, and that is why we consider any value where the derivative is undefined a critical value.